All right, everyone, this is lesson 2.3, polynomial functions. So a little bit about polynomials. So we just have some examples of polynomial functions and non-polynomial functions. So to be a polynomial function, you need a whole number exponent. So right here, you can see that this has a fraction in the exponent, so that makes it not a polynomial. You also can't have a negative in the exponent. You also can't have division by a variable right here. We have division by a variable. So these are just some examples as what makes it not a polynomial and what makes it a polynomial. So you need positive whole number exponents. So a little more, you notice for polynomial functions, the graphs are smooth and continuous, so there's no breaks. So you can see smooth rounded corners. They continue, there's no breaks. The graphs of not polynomial functions. I'm sorry, not the graphs of polynomial functions. They're discontinuous, which means there are breaks or they have sharp corners. So polynomial function graphs are continuous round corners. Not polynomial graphs are discontinuous and they have sharp corners. So the first thing we're going to talk about is the leading coefficient test. So we use the leading coefficient test of a polynomial to determine its end behavior. So that means, is it going to go, rise left, rise right, fall left, fall right? So we can just look at the leading coefficient. So that's going to be the first term with the highest exponent. So, and it doesn't have to be the first, but it's the one with the highest exponent. So you look, if it has a positive a value, so we're looking at something like that, a positive a value and an even exponent. So a positive a value and an even exponent. It's going to rise left, rise right. So a polynomial with a leading term that has the highest power, that is a positive a value, and n, which would be the exponent, is even, it's going to rise left and rise right. So an example that we could think of is x squared. If you look at x squared, the a value, which is 1, is positive, and the exponent is even. So even exponent, positive a value. Now let's talk about if you have a even exponent and a negative a value. That is going to fall left, fall right. So again, if you look at, as an example, negative x squared, right? Negative x squared has a negative coefficient and an even number exponent. Now let's talk about if you have an odd exponent. If you have an odd exponent and a positive a value, you're going to fall left, rise right. So the example I always use is x cubed. So x cubed has a positive a and an odd exponent. And if you think about it, negative x cubed is going to rise left and fall right. Because the odd exponent and the negative a value. So what you really need to know is all right here. And always break it back down to x squared and x cubed. All right, so we got a couple different polynomials here. Now we're going to use the leading coefficient test to determine the end behavior. So for this one here in the top left, we have an odd exponent, positive a value. So that means this is going to fall left. Rise right. It's going to fall left and rise right. Okay. Right here under it, we have a positive a value and an even exponent. So this one is going to rise to the left and right. So why don't you guys pause the video and try to do the ones on the right. All right. So these two on the right were a little tougher, only because they give it to you factored. So you have to think to yourself, what is the exponent going to be? What's going to be the degree? So because here we have a degree 3, here we have a degree 2, and here there's a degree 1. This is going to be a degree 6 polynomial. 6 is even. The a value is -4. So that means you have a negative a and an even exponent. So it's going to fall to the left and the right. So again, I figured out what the power was. So we have x to the third squared and 1. So that tells you that is a degree 6 polynomial. The leading term is negative, the coefficient, so it falls left and falls right. Down here, we have 3, 1, and 1. So that makes it a degree 5 polynomial. We have a positive a value, which is 2. So that means it's going to fall left and rise right. So again, you figure out what the degree is. You look at the a value if it is negative or positive, and then you can determine the end behavior. So that's using the leading coefficient test. All right, so we're going to do a rough sketch of the given polynomial. So it is written in factored form. So that tells me there are x-intercepts at x equals -1, x equals 5, and x equals 3. And I got those numbers by setting each factor equal to 0 and solving for x. So now I'm going to put dots at -1, 3, and 5. So those are my roots, my x-intercepts. Now I'm going to look at the end behavior. Because we have x times x times x, that tells me this is going to be an x cubed is going to be the first term. It is positive. So this is going to have an odd exponent. A value is going to be greater than 0. So that tells me this graph is going to rise right, fall left. It's going to look something like that. Now, if you notice, this is a rough sketch of the function. If you notice, there are, I'm going to bold them in, 1, 2 turning points. I'm going to point with my fingers. These are the 2 turning points. How do we know how many turning points? If n is the degree, there are n minus 1 turning points in the graph. So if n is the degree, there are n minus 1 turning points. So for this is a degree 3. So there are two turning points. The next thing we can talk about here is multiplicity. So multiplicity is how many of those roots are there. So if you look, x plus 1, there's only 1. X minus 5, there's 1. X minus 3, there's 1. So this right here has an odd multiplicity. It has an odd multiplicity. So that means at each x-intercept, the graph is going to cross the x-axis. So this has an odd multiplicity because look, first power, first power, first power. So it has an odd multiplicity. So at each x-intercept, the graph is going to cross. So if you look, the graph strikes through each x-intercept. Strikes through the x-axis at the x-intercept. So the graph is going to cross the x-axis. So that's how you make a nice little rough sketch. All right, next one here. We're going to figure out our zeros, our x-intercepts. So this is going to be x equals 1, x equals negative 2, and x equals 2. So I'm going to put little dots at 1, at negative 2, and at 2. So this is going to be a degree 4 because we have x squared, first power, first power. So this is a degree 4, and the a value is negative, or it's a is less than 0. So that means it's going to fall left and right. So it's going to fall left and it's going to fall right. We learned from the last slide that there are n minus 1 turning points. So since this is degree 4, there are 4 minus 1, which equals 3 turning points. Now, there is a little something that we need to realize. You see this 0 that I'm going to circle, x minus 1 squared. That 0 of x minus 1 squared, where x equals 1, has an even multiplicity. The others have odd multiplicities. So this has an even multiplicity. So when something has an even multiplicity in the graph, on the graph, the graph touches the x-axis at that x-intercept and turns. So it's going to touch it and turn. So at x equals 1, it's going to touch it and turn. At x equals negative 2, I'm going to go right through. At x equals 1, watch my pencil now, I'm going to touch it and turn. And then at x equals 2, I'm going to cross. So because this x equals 1 has an even multiplicity on the graph, it doesn't go through the x-axis at that point. It touches it and turns. The other ones have an odd multiplicity, so it strikes through. So what we need to remember is that even multiplicity, touch and turn. Odd multiplicity, it goes through, or it crosses. So I'll put a little cheat sheet down here. even multiplicity, touch turn, odd, cross. So that's just a rough sketch. All right, finding the zeros of the polynomial functions. So when we find zeros, we have to take the function and set it equal to 0 first. For this one, we are going to use the strategy of factoring by grouping. So this is going to be a group, and this is going to be a group. So first thing I need to do is take the GCF out of each group. The GCF is the greatest common factor. So what do these two terms have in common? The biggest thing I could pull out is an x squared. When I take an x squared out of x cubed, I have x. When I take an x squared out of 2x squared, I'm left with plus 2. The next group, the GCF is -4. I take out a -4, I'm left with x plus 2 equals 0. Inside the parentheses here should match. That means you did it right. And then your groups are the outsides and the inside. That is how you factor by grouping. This can actually be factored more. X squared minus 4 can be broken down into x plus 2 and x minus 2. And then the x plus 2 from the top. And then we can rewrite it as x plus 2 squared, because there are 2 of them, times x minus 2. So that is completely factored. This one is x equals -2, and this is x equals 2. This right here is an even multiplicity, so you know if we were to graph it, it would touch and turn. This one would cross. So that is factoring by grouping. Over here, we could start with GCF again. Set it equal to 0. Pull out an x squared. Leaves me with x squared minus 4. Equals 0. Then I can again factor this into x plus 2, x minus 2. Now when you get here, I know I kind of breezed through it in the last one. You're really setting each factor equal to 0 and solving. So x squared equals 0, x plus 2 equals 0, x minus 2 equals 0. So this means you have a 0 at x equals 0, x equals -2, and x equals 2. In the example on the left, I kind of skipped that step just because I thought we should know it, but I wanted to show you that this x squared in the front means that x equals 0. So that is how you find all the zeros. You factor. All right, now we're going to put it all together. We're going to use everything we learned for this function. So the first thing we're going to do is the leading coefficient test. So end behavior. This end behavior, because it is degree 3, which is odd, and has a positive a value, the end behavior is going to look like that. It's going to fall left, rise right. Next thing we're going to do, x intercepts. So we're going to take x cubed plus 3x squared minus x minus 3. Set it equal to 0. Now, because we have 4 terms, we're going to factor by grouping. So this is a group and this is a group. The GCF of the first group is x squared. When you take out an x squared, you're going to have x plus 3. Of the second group, the GCF is -1. You're going to pull that out. You're going to have x plus 3 equals 0. You're going to make your groups x squared minus 1 and x plus 3. This can be factored again into x plus 1, x minus 1, and then you have x plus 3 equals 0. So this is x plus 1 equals 0. This is x minus 1 equals 0. And that is x plus 3 equals 0. So this x-intercept is x equals -1, x equals 1, and x equals -3. So that's how you factor to find the zeros. So now I'm going to plot them all. So x equals -1, x equals 1, and x equals -3. So those are my zeros. I know based on the end behavior, it's going to end up something like that. Next thing we can do is y-intercept. The y-intercept is going to be 0, -3, because if you were to do 0 cubed plus 3 times 0 squared minus 0 minus 3, you would just be left with -3. So the y-intercept is going to be here. Let's check our multiplicity. Multiplicity is going to be all odd. So all crossing x axis. And then our turning points is n-1. This is a degree 3, so it's going to be 3 minus 1, which equals 2. So your rough sketch can look like this. Oops, I'm sorry. The y-intercept is -3. That's my fault. And that is your rough sketch. So that's putting everything together. All right, last one, putting it all together. So first thing we're going to do, leading coefficient test. This is going to fall left, fall right, because a is less than 0. And we have an even exponent. For the x-intercepts, -x to the 4th plus 4x to the 3rd minus 4x squared equals 0. You're going to pull out a GCF. Your GCF is going to be -x squared. So when you do that, you're going to have x squared minus 4x plus 4 equals 0. You can actually factor that. So -x squared times x minus 2, x minus 2 equals 0. Now, because there are two x minus 2's, you can rewrite that as x minus 2 squared equals 0. So that tells you that you have a 0 at x equals 0 from here and x equals 2 from here. So I'm going to plot those. 0, 2. My end behavior is down and down. So now, if you look at the zeros, let's do our y-intercept first. Y-intercept is just going to be at 0, 0. Because if you do f of 0, you will get 0. Now let's look at the multiplicities. So if you look at the roots, -x squared and x minus 2 squared equals 0. They both have a multiplicity of 2. So they are going to both touch and turn. Even multiplicity. And there should be how many turning points? n-1. 4 minus 1 equals 3. So when you graph this, if you watch my pencil, I'm going to get here. I'm going to touch turn. Now I'm on my way back. I know I have to hit this 0, so I have to turn again, touch turn, and come back down. So it kind of looks like an M. But if you look, there are 1, 2, 3 turning points. And that is putting it all together. Sorry for the long video.